Welcome back, students. In the final two lectures of class, we will investigate complex reaction mechanisms. So let's jump right into it. We'll start today by getting an introduction to these complex reactions. The learning goals for today are going to be to evaluate complex mechanisms, to compare them to the experimentally determined rate laws and make sure that they mesh and are appropriate. Then we're going to look at some other complex mechanisms. We'll look at the pre-equilibrium approximation, which is another approximation, much like the steady state approximation, that helps simplify these problems. We'll look at the Lindemann mechanism, which actually predicts how unimolecular reactions are possible under different circumstances. And then briefly at the end, we'll look at catalysis and adsorption. We'll start here by considering what we mean with a complex reaction. Complex makes it sound hard, but a complex reaction is simply a reaction that occurs with two or more elementary kinetic steps. So in the last chapter, we looked at a lot of elementary kinetic steps, but here we're looking at mechanisms that proceed by more complicated scenarios. So consider this reaction shown here. We have two molecules of N2O5 reacting with each other to make 4 molecules of NO2 and 1 molecule of O2. A naive assumption into this would be that this is a bimolecular reaction. You have 2 molecules of N2O5, they collide and fragment into all of these products. However, if we actually measure the rate of this experimentally, we can determine that the experimental rate law for this is first order with respect to N2O5. And that tells us that a bimolecular collision is not the way that this goes forward, but somehow one molecule of N2O5 is actually driving this rate. So that means the bimolecular collision is not possible, and we have to look for a more complex mechanism to describe this. And so we'll go to the board and try to identify it. The proposed mechanism for this reaction is as follows. We start by taking a single molecule of N2O5, and we put this in equilibrium with a rate of K1 and K minus 1 to making 1 molecule of NO2 and 1 of NO3. So this N2O5 decomposes into NO2 and NO3. Then we take the molecules of NO2 and NO3 and allow these to collide together with a rate K2 that makes NO2, O2, and NO. Finally, we take a molecule of NO and a molecule of NO3, collide them together with a rate K3 to make 2 molecules of NO2. Since we have 2 NO3s over here in our reactant side, we're going to need to double this first reaction. This gives us a balanced chemical reaction. We have 2 N2O5s as our reactants. For our products, we should have 4 NO2s, and we have 2 NO2s here. We consume 1, and we have then 1 and 2, 3. So we make 5. We consume 1 for a total of 4. We make 1 O2. We have 2 NO3s being formed, which are both consumed, and 1 NO being formed that is also consumed. So this is a balanced chemical reaction. Now, it's likely not immediately obvious to you that this mechanism provides a first order reaction with respect to N2O5. In order for us to actually determine that, we have to evaluate what the rate law for this reaction would be. And remember, what we're trying to do is make sure the mechanism agrees with the experiment. If the mechanism agrees with the experiment, the rate law is reasonable and may actually be correct, although agreeing with the experiment is not enough to ensure that a mechanism is actually correct. How would we describe the rate of this reaction? Well, we can describe the reaction rate as simply -1/2 times the loss of N2O5. The 1/2 here comes from the stoichiometric coefficient of 2. So we can describe what the loss of N2O5 is. And the loss of N2O5 we can describe as K1 times N2O5. So K1 times the concentration of N2O5. That's how we lose N2O5. The only way to make N2O5 is by K negative 1 times NO2 times NO3. And so this describes the rate of our reaction. To solve this rate, we need to know what the concentrations of NO2 and NO3 are. And we'll figure this out by using the steady state approximation. So the steady state approximation says that all of the intermediates don't change their concentration, so the rate of change of concentration of the intermediates is equal to 0. The intermediates of this reaction are NO and NO3. So we can say that the change of NO with respect to time and the change of concentration of NO3 with respect to time are equal to 0. And this will allow us to get estimations for what these concentrations are. So what's the rate of forming NO? Well, NO is formed in this second process here. NO is formed by the rate of K2 times the collision between NO2 and NO3, and NO is consumed by the rate K3 times NO times NO3. NO3 is produced based on the rate of making K1 and N2O5. And it is consumed by K minus 1 times the concentration of NO2 times the concentration of NO3. It's also involved in the second and third steps. So NO3 is also consumed based on K2 times NO2 times NO3. And it's also consumed by K3 times NO and NO3. So these two expressions tell us how NO and NO3 are produced and consumed. We can rearrange these equations. So if we rearrange this first equation here, we can add this term to the other side and divide by NO3 to find that the concentration of NO is simply equal to K2 over K3 times the concentration of NO2. With the other reaction, what we can do is bring all of these guys to the other side of the reaction. So this will give us K1 N2O5 is equal to K minus 1 NO2 times NO3 plus K2 times NO2 times NO3 plus K3 times NO times NO3. But we just figured out that NO can be written in terms of NO2. So that allows us to factor out NO2 times NO3 from all of these equations. And what we have left is then K minus 1 plus K2, and then plus K3 times K2 over K3. Or K minus 1 plus 2K2 times the concentration of NO2 times the concentration of NO3. So now we have another expression for what NO2 times NO3 is. If we divide both sides of this equation by K minus 1 plus 2K2, we find that the concentration of NO2 times the concentration of NO3 is equal to K1 divided by K minus 1 plus 2K2 times the concentration of N2O5. We can now plug this in here for what we didn't know before, the concentration of NO2 times NO3, to allow us to actually solve the rate. So the rate is then equal to 1/2 times K1 times the concentration of N2O5 minus K minus 1 times K1 over K minus 1 plus 2K2 times the concentration of N2O5. Now we can factor out the N2O5 here. I'll do some simplification. What we end up with is K1, K2 over K minus 1 plus 2K2 times the concentration of N2O5. In other words, we have a K effective times N2O5, or a first order reaction. So this reaction, despite being a complex reaction, we can come up with a mechanism that predicts the experimentally determined rate law of first order with respect to N2O5. Like we saw, this is complicated. So it's not, the math that we can do is relatively straightforward, but proposing a mechanism like this takes intricate knowledge of the actual reaction at hand and is not something that you could do as senior chemistry students on an exam, certainly. It takes a lot of understanding of the chemical reactions that you're working with. We'll look next at what's called the pre-equilibrium approximation. So let's go back to the slides and see the pre-equilibrium approximation. Consider the reaction where we have two reactants, A plus B, that could be in a reversible reaction to make an intermediate I, and then the intermediate I goes to product P. If product formation is slow, that means that A and B will make I, and I will go back and make A and B, and this will happen much more rapidly than the product is formed, which means that before we get any product, we have a pre-established, a pre-equilibrium between the intermediate and the reactants. Why is this important? Well, because we can simply represent the concentration of intermediate with the equilibrium constant. So the equilibrium constant, we could describe that as the forward rate over the reverse rate, but we can also describe it as the concentration of intermediate product over the concentration of reactants, A and B, just like we always have described equilibrium constants since high school. With this, we can say that the rate and change of our product with respect to time, or the rate of the reaction, which is simply equal to the rate of product formation times the concentration of intermediate that forms product, we can now represent this concentration of intermediate based on the equilibrium constant, or the rates if you prefer, times the concentration of A and B. So just like the steady state approximation, this approximation allows us to essentially get rid of the intermediate concentration and put in the reactants that we can more easily measure. Unlike the steady state approximation, this doesn't assume that the reaction, that the intermediate doesn't change, but it assumes that the conversion between reactants and intermediate is faster than the conversion between intermediate and product. So it's appropriate under a different set of circumstances. In the homework, you will go through an example problem using the pre-equilibrium approximation. A classic example of complex reaction mechanisms is the Lindemann mechanism for unimolecular reactions. So this is a mechanism that shows how a single molecule can actually get enough energy to interact, usually in the form of an isomerization or a decomposition. So we might assume that a molecule doesn't have enough energy to normally react, which is why it's not normally reactive and exists in its certain state. However, if it collides with another molecule, perhaps that collision can give it enough energy to actually overcome an activation barrier and react. We therefore might expect the reaction rate to be a second order reaction, where we have to have two different molecules collide with each other to actually give enough energy. However, for these types of reactions, the experimental rate law is often only first order. So it just appears that one molecule all by itself somehow acquires enough energy to decompose or isomerize or something like that. How can we actually recognize or reconcile these? We'll go back to the board and try to address this and understand the Lindemann mechanism. We'll start by assuming that we actually do need a collision in order to provide a molecule with enough energy to fragment or isomerize. When a molecule acquires this energy, it can either form products or collide with another molecule and revert to its low energy state. We can write that mechanism as the following. We have two molecules of A, and those are involved in a bimolecular collision with rate K1 that forms what we'll call A star and another A. So this A star is an activated molecule of A that has enough energy to react. There are two options for this A star. This A star can hit either the same or another molecule of A and revert. So we'll go back down to A plus A. So no reaction happened here. Let me be a little bit clear. This is K minus 1. Another possibility is that this molecule that has enough energy can also just react and form the products, whatever they are, with a rate of K2. The rate of this reaction is therefore the change in the concentration of product with respect to time, which is simply the rate constant K2 times the concentration of the activated reactant A star. In this reaction, our A star is an intermediate, so we will apply the steady state approximation. The steady state approximation says that the change in the concentration of our intermediates with respect to time is equal to 0. And how do we form this A? Well, we form this A by K1 times A squared, a bimolecular reaction. And we consume this A star either in K minus 1 times A star times A. We also consume this by K2 times A star. So putting these together and rearranging, we can say that the concentration of A star is simply equal to K1 times the concentration of A squared divided by K minus 1 times the concentration of A plus K2. So I simply added these two terms over to the other side of the equation, factored out the A, and then divided by the remainder there. We can plug this in to get an expression for the rate. So if we plug this guy back in up here, we find that the rate is equal to K2 K1 times the concentration of A squared divided by K minus 1 times the concentration of A plus K2. Okay. So what happens to this rate as a function of A? At high A concentrations, so if we have high concentration of A, K minus 1 times the concentration of A is going to be much greater than K2. In that case, we can approximate this by saying that the rate is approximately K2 K1 times the concentration of A squared. And then if K minus 1 times A is much greater than K2, we can ignore K2, which allows us to say that the rate is equal to K2 K1 over K minus 1 times the concentration of A. In other words, the reaction would appear to be a first order reaction. However, if we have low concentrations, so at low concentrations of A, K minus 1 times A is going to be much less than K2. And so in that case, we can approximate the rate as K2 K1 A squared over K2, or K1 times the concentration of A squared. So at low concentrations, the reaction would appear to be second order. We can make a different assumption that it doesn't have to be the same molecule of A that it collides with, but just some random molecule M. And we've done this in the slides. So if we go back to the slides, we come up with this expression here. This is basically the same expression, except for the random collisional partner is taken not to be another molecule of A, but taken to be M, as shown here. And we can pull the rest of this out to get some unimolecular rate constant times A. So it works exactly the same as we just saw on the board. If we have very high concentrations, K minus 1 times M is greater than K2, and the M's will cancel out, and the rate, this K uni here, should be independent of the pressure. And we can see that up here. So at high concentrations, the rate is independent of increasing concentrations. However, at low concentrations, we can ignore this term and we get K1 times A times M, and we should have a linear dependence. And we see that here as well. So this Lindemann mechanism has been verified Essentially, it says that if you have very high concentrations, there's so many collisions that it's essentially a first order process. But if you have low concentrations, you don't have very many collisions. And so the collisions are rate limiting, and that can slow down the actual rate. Lastly, we're going to briefly consider catalysis and adsorption. So we've seen a lot of catalysis before, particularly in biochemistry class. We all are pretty comfortable as senior chemistry students stating that a catalyst is something that speeds up the rate of a reaction that is not consumed in the reaction, and it does this by lowering the activation energy. We can set up a reaction scheme for this, and this is basically the exact same scheme that we just had for our pre-equilibrium approximation. We have S plus C in equilibrium with a substrate catalyst complex, and then that forms a product and releases the catalyst unchanged. Using the familiar approach that we've been using in the past few lectures and the steady state approximation, we can represent the rate as simply K2 times the concentration of our substrate catalyst complex, our intermediate here. And then we can use the steady state approximation to break this down into K2 times K1 over K minus 1 plus K2 times the concentration of substrate times the concentration of catalyst. And we can simplify all of this into Km. You'll recognize Km from Michaelis-Menten kinetics. Just like in Michaelis-Menten kinetics and every other thing we've been talking about in the past few lectures, the rate will change as a function of reaction as the concentration of substrate changes. So we can define the concentration of substrate as the initial concentration of substrate minus the substrate in complex with the catalyst minus the product. And we can define the concentration of catalyst as the concentration of initial catalyst minus the substrate catalyst complex. And using this, we can bring this all together to find an initial rate, which we can define as K2 times S naught times C naught over S naught plus C naught plus Km. And under the condition we're most familiar with, that is the substrate is much greater in concentration than the catalyst, we can essentially ignore this catalyst concentration to have K2 times S naught times C naught over S naught plus Km. And this is the way we can describe the rate of a reaction. Note here the similarities between this and Michaelis-Menten enzyme kinetics. The only difference really is this is talking about a rate of the reaction, whereas Michaelis-Menten enzyme kinetics talks about the initial velocity. So there's some slight differences in terms of the nomenclature there, but it's basically the exact same thing we're very familiar with deriving. The book goes into much more detail about catalysis and a lot with Michaelis-Menten enzyme kinetics. We're going to leave that for biochemistry, and I assume you guys have worked that to death in previous courses. Lastly, here we'll touch on adsorption for the similarities with Lab 7. So adsorption, we're going to look at through the view of the Langmuir isotherm. And we've heard this word isotherm before. Maybe we don't know what it means. An isotherm, what we're saying with this is that the kinetics, the properties of this graph will change as a function of temperature. So another way that I've commonly heard isotherms are again in things like enzyme kinetics, where we have a certain plot of how the enzyme works as a function of substrate concentration. But if we were to change the temperature, the kinetics would change. We'd have a different isotherm. So we're assuming that all points in the plot have the same temperature. So they're isothermal. That's where the isotherm comes from. The Langmuir isotherm assumes a couple of things, and we talked about this in Lab 7. It assumes that we have monolayer coverage of the adsorbent, and the absorbate only sticks on a single layer, so we don't stack on top of other adsorbate molecules. We also assume that there's a uniform surface that doesn't change how the adsorbate sticks onto the adsorbent, so they're all sticking at every spot equally. And we then finally assume no cooperative binding. Cooperative binding would mean that one molecule would recruit more molecules to the surface, and we assume that that is not happening. If all of these assumptions are appropriate, we can say that the change in the fraction of sites occupied with respect to time is going to be equal to 0, since that's we're at equilibrium. And at equilibrium, then the rate of forming these must be equal to the rate which it leaves. So this is Ka is the rate at which molecules adsorb onto the surface. Kd is the rate at which molecules deadsorb. A is the concentration of our adsorbent. So we have the rate at which they absorb times how much there are, and then times n times 1 minus theta, which is how many open spots are there. So they will bind based on how fast it happens, how many molecules there are to bind, and how many binding sites are still available. They will desorb based on the same thing. So how many how fast they desorb. N is how many sites there are, and theta is how many are occupied. So how many occupied sites there are. We can put these together and solve for what theta is, the fraction bound, and we can eventually come up with this equation that's equal to K, where K is the ratio of adsorbing to desorbing, times the concentration of A over K times A minus 1. And this gives us the Langmuir isotherm like we've used in lab 7. In the last lecture of the class, we'll continue talking about complex reaction mechanisms to look at radical chain reactions.